Today we study electric field and electric charge. Electric charge Q emits electric field. If it is positive, it emits electric field, and this is a positive. If it is negative, Q is negative, then electric field enters. So positive case is the source of electric field. Negative charge is the sink of the electric field. A physical field is a function of position that is either a scalar or a vector. The field is different from mathematical field. Field is a function of position vector. And sometimes this field is a scalar. For example, temperature field or potential field. And sometimes it is a vector. Function of position vector, but the value is a vector. This is vector field. It is also possible to have time dependence, then time dependent scalar field, and this is a time dependent vector field. So anyway, field is a function of position that is either a scalar or vector. If it depends on time, then we call it a time-dependent field. So this is time-dependent scalar field, and this is time-independent scalar field. Time-dependent vector field and time-independent vector field. Otherwise, we call it time-independent field. A temperature field and a pressure field are scalar fields because temperature, pressure, they do not have the direction. They have magnitude only. So the value of the function is scalar. So we call it scalar field. An electric field and a gravitational field are vector fields because they have both direction and magnitude. The electric field symbol of the electric field is E, capital E. At any point is defined in terms of electrostatic force F. We learned that Coulomb's law force between two charges is 1/4 pi epsilon 0 Q1 Q2 divided by R squared, and the direction is along the straight line connecting Q1 and Q2. If the two charges are of equal sign, then the force is repulsive, and if the sign of the charges are different, the product is negative, then the force is attractive. Electric field is defined in such a way that the force divided by charge. For example, we have some electric field E is present. If we have a charge Q equals 1 Coulomb and charge capital Q is 10 Coulomb, for example, then the electrostatic force is electric field multiplied by the charge. So this is the electrostatic force applied by the electric field to the point charge small q. Under the same electric field, the force changes, these are the same, comma, however, because the two charges are different, we have electrostatic force depending on the charge. Unit of the electric field is Newton per Coulomb. The unit of the electric field is the unit of the force is Newton, unit of a charge, electric charge, Coulomb. So Newton per Coulomb. The electric field is independent of the test charge. So we call this small q or capital Q, test charge. Electric field lines. Michael Faraday first introduced the concept of field lines. Field lines. Field line is if there is a positive charge, electric field line is like that. If there is a negative charge, electric field line enter. What happens if we have two charges? For example, if we have positive and positive electric field line, we have two sources. And the resultant electric field line due to these two charges can be evaluated by a vector sum. B. Electric field lines extend away from positive charge. Extend away from positive charge. And extend toward negative charge. Extend toward negative charge. C. At every point around the positively charged sphere, an electric field vector points radially out of the sphere. If it is a sphere, electric field line is normal to the surface. Okay? Electric field line. So, points radially. This is a radial direction. D. At every point around the negatively charged sphere, an electric field vector points radially toward the sphere. Right? If it is a sphere, this is a positive and negative, then enters into the sphere. E. The electric field lines extend away from a conducting sheet along the normal. What happens if it is a conducting sheet? Conducting sheet, electric field is normal to the sheet. Okay, normal direction. If it is a positively charged, left side, normal, and extends away. Okay, what happens if I have negatively charged plate? negative charged plate, electric field line approaches the surface. The direction is normal to the surface. Alright. F. The electric field vector must be tangent and parallel to the field line. Because electric field is additive, for example, if we consider these two sources, two positively charged sources of the electric field, the electric field line is the sum of the sum of these two contributions. So if I combine these two, this contribution, and sum is this one. So in the middle of the pie chart, in this place, electric field line extends away. In a similar manner, at this point, electric field line due to the right charge is this, electric field due to the left charge is this, and resultant electric field is like that. Okay. In such a manner, we can combine the two contributions to find this kind of form. Right? So positive, positive. What happens if I have positive and negative? Then the electric field lines this way. Something like that. All right. Therefore, at a certain point, if the electric field line is curved, electric field is tangent. So at this point, tangent to the electric field line is E field, electric field, and electric field line. Electric field line. It's electric field line, and electric field at a point is tangent to the electric field line. All right. A closer spacing of the field line means a larger field magnitude. So the electric field line is dense. For example, here, strong field. Here, weak electric field. Right? The closer spacing, larger field magnitude. Number 3, the figure shows the field lines for two identical positively charged, positive, negative. What happens to the negative and negative? In case if we have negative, then the direction is opposite. Okay? Negative. 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 All right. In summary, the electric field lines are invariant under the rotation about the symmetry axis. Here, these two charges are of equal magnitude. So, there is a symmetry axis. This is a symmetry axis. So, we have above the symmetry axis and below the symmetry axis, the two figures identical to each other. B, the density of the field lines is proportional to the strength of the field. Density of the field lines. So we already know the density is higher, the field is strong. Density is sparse, then the strength of the electric field is weaker. C. The number of electric field lines should be the same for any charge of the same amount. So, plus, for example, if I have 1 coulomb, if we draw 4 electric field lines, the 2 coulomb, we draw double the number of field lines. Okay? So the number of field lines should be the same for any charge of the same amount. The field lines never cross. Electric field line never cross. This is wrong. Never cross. Electric field lines never break. Electric field lines stop, go, impossible. They should be continuous. They should be continuous. Except that source, sink, it begins at source that is positive charge and it stops going and it enters into the negative charge that is sink. Or a spherical conducting shell of net charge 0, shell is a sphere, empty sphere. Shell of net charge 0 surrounds an isolated positive point charge at the origin. This is shell and conducting shell. And we have a point charge at the center, plus Q. Then electrostatic force the plus Q is placed at the center. This positive charge attracts the negatively charged particles on the shell. So just inside the shell, negative charge is induced. But you know, the charge is conserved. So neutral initially the shell was neutral. Therefore, there should be positive charges. Because of the Coulomb repulsive force between positive charges, these positive charges are just outside the shell. And the induced charge, the amount of induced charge is the same, except for the sign. So the amount of charge just inside the shell is minus Q, and the amount of charge just outside of the shell should be plus Q to make the sum to be 0. So A, the negative charge minus Q is uniformly induced over the inner surface of the shell. B, the positive charge plus Q is uniformly induced over the outer surface of the shell. The outside of the outer surface of the shell, the electric field lines are the same as the case without the presence of the conducting shell because of the shell theorem. There used to be the electric field lines originally, but after redistribution, what happens? If we consider this shell, a little bit bigger shell, then the amount of charge, net charge is plus Q, just like this. So outside electric field line is like that. According to the shell theorem, there is no electric field inside a conducting shell. So inside the shell, the electric field vanishes. The same number of field lines passes through shells because the field lines never cross and never break. Okay? Because of the spherical symmetry, the electric field lines are radial. Right. Spherical symmetry is rotational symmetry about any axis. If you rotate about any axis passing this center of this shell, there should be no change. So this system is invariant on the rotation about any axis passing through the center. So that is a spherical symmetry. Because of that, the electric field must be radial direction. Or a spherical conducting shell of net charge 0 surrounds an isolated positive charge. This is the same problem. 5. The diagram shows the electric field lines between two charged parallel metal plates. Metal is a conducting plate. Conducting plates. The electrostatic force on a proton at X, proton is placed in here, is the same as that of Y. You find the spacing of the electric field lines are uniform. So here and here, electric field E is uniform. However, this is curved. For example, at this point, the electric field line is like that, and it is because it is tangent, it changes its direction. But in here, spacing is the same, so magnitude and direction, they are invariant. So the electric field lines are parallel in the middle, right? In the middle, electric field lines are parallel. Curves at the edges of parallel plates. At the edge, electric field lines are not parallel, but they are curved. Okay? You remember, just point charge, electric field lines is like that. Okay? However, it is a plate is big enough. In the middle, electric field lines are uniform. 6. The diagram shows the electric field lines between two charged particles y and z. Y is a positive charge, positive, because electric field lines comes out of y, so it is a plus. It enters into z, so this is a minus. Z must be negative. Because the electric field lines are symmetric about the axis connecting y and z, this is not exactly true because, for example, if we have plus plus, they are not symmetric. I mean, according to the symmetry, rotational symmetry about rotation about this axis, this part, this part, this part, this part, the electric fields are the same. That's fine. However, if they are not symmetric, for example, is not something like that. Okay, so there is another symmetry axis that is perpendicular to the straight line connecting the two charges. If there is a left-right symmetry, then the two charges are the same. If it is not the case, electric field lines does. Oh, this kind of asymmetry may arise. Okay, if Q and Q, if Q absolute value of Q is not equal to absolute value of a small q. But we have left-right symmetry, so we say these two charges are the same. Monopole electric field. Electric field due to a monopole can be obtained directly from the Coulomb's law of force. You remember the electric field can be evaluated by dividing the Coulomb force by the amount of charge of the test charge. So this Q is the source, and if we have a test charge Q0 at some point, then the electrostatic force can be computed by making use of the Coulomb's law of force, and then divide this charge Q0, you'll find the electric field. So electric field is exactly the same as the Coulomb force, except that we have replaced QQ0 with Q. So we have removed the amount of charge for the test charge. The magnitude of the electric field is independent of the test charge. Right. This test charge has been cancelled out, so it depends only on the source charge. This is source of the electric field. The direction of the electric field is independent of the sign of the test charge, because Q0 is independent of the electric field. It is independent of the amount of the Q0 as well as the sign of Q0. A point charge is at the origin, and the electric field at R is E. N is the non-vanishing integer. Okay. A point charge Q is at the origin. There's a vector R, and at this point you measure the electric field. You multiply n to the radius position. Then electric field here depends on the R, so we replaced R with nr, so we have 1 over n squared suppression. Sure, if you replace R with R over n, then it is magnified by a factor of n squared. Okay, let us consider problem 5. Electric field can be added. That is the superposition principle. Just like we can add up all forces applied to a single particle to compute the net force on a particle. We say it is a superposition principle. Superposition principle holds so when we consider F0 be the electrostatic force on the test charge Q0 due to n charges. Suppose that Q0 is placed at here, and we have Q1, Q2, Q3, and Qn. And there should be the electric field due to Q1, electric field due to Q2, electric field due to Q3, and the electric field due to Qn. So E1 0, E2 0, E3 0, En 0. So net electrostatic force due to the N charges applied to the test charge Q0 can be expressed in terms of the sum. And the electric field can be computed by dividing the electrostatic force by the amount of test charge Q0. So electric field can be computed dividing this F0 by the test charge Q0. The answer is sum of the electric fields. So sum of these electric fields. So this EK represents the expression. Okay. So you can compute the electric field due to various charges. So you can compute the electric field at the origin. You need to compute the electric field due to discharge Q2, due to discharge Q1, and due to this Q3. It depends on the sign. Q1 is negative, hence the electric field, this one, is in this direction, and Q2 is positive. And amount of charge is double, so E2, E1, and E3. So what you need to do is to add up these vectors down. And detailed calculation is given in here. Okay, let's consider the dipole electric field. Until now, we have considered the electric field due to monopole, and dipole is plus Q and minus Q, plus Q and minus Q, separated by distance d. So we define dipole moment as Q d vector, and here vector d has the direction from the negative to positive. Okay, dipole is consists of two equal charges in magnitude but opposite in sign. And if the separation between the two charges is d, and the product charge q multiplied by the distance and the displacement vector from the negative charge to the positive charge, d, qd, is dipole moment, electric dipole moment. Okay, a monopole Q is placed in here. The strength of the electric field is proportional to 1 over r squared. We know this minus Q, for example, 1 over 4 pi epsilon 0, electric field, 1 over 4 pi epsilon 0 is a plus Q and minus Q. If they are placed at the same place, the electric field, some of this electric field cancel. Therefore, the final result for the resultant electric field due to the electric dipole cancels. 1 over r squared dependence cancels, and it decays faster than 1 over r squared. That means 1 over r cubed. Electric field due to dipole is proportional to 1 over r cubed instead of 1 over r squared because of large cancellation. Consider a function f of x, 1 of x equals to 1 of x squared. So you can follow this simple, straightforward mathematical calculation. This is the proof that the leading term is cancellation. You'll find the dipole electric field decays faster than that of the monopole. That means 1 over r cubed instead of 1 over r squared. Okay, let's consider the next problem. Consider the electric field lines in the presence of an electric dipole. We have plus and minus of equal sign. We will find left-right symmetry. And in the middle, up and down symmetry, and left and right symmetry. So they are of equal charge except for the sign. So electric field comes out of the positive charge, enters into the negative charge. So this is electric dipole. An electric dipole consists of two charges. One is a plus, the other is a minus, but the magnitude are the same. Separated by a distance d here from negative to positive, we have d vector. So dipole moment, electric dipole moment is d times q, when this is plus q and this is minus q. Okay. The electric field lines emit from plus q and enter into minus q. Correct? The electric field E at a point is tangent to the electric field line passing that point. Electric field line tangent to the electric field line. So this is the electric field. At this point, O. This is positive. So at this point, something like that. At this point, electric field line. At this point, tangent. Okay. C. The electric dipole moment P is defined by, we already have discussed about this. Number 3, the electric field due to an electric dipole. Let us consider the z-axis. And we have z plus 1/2 d, z minus 1/2 d, and this is origin. We compute the electric field at point z, point 0, z. No, the distance from this point to there is z minus 1/2 d, and this distance from the negative charge, so positive charge and negative charge, this is z plus 1/2 d. Okay, electric field at point P due to this positive charge is 1/4 pi epsilon. This one is the same, distance square, and different charges. Electric field due to the positive charge should be along this direction. Electric field, this negative charge, should be along this direction. You know, it's closer. Therefore, electric field due to the positive charge, if z is a positive and z is greater than z plus, then the strength of the electric field due to the positive charge is greater than the electric field due to the negative charge. So the resultant electric field should be smaller than the original strength due to either positive or negative. But the difference is like that. So electric field, the net electric field is smaller than the pure monopole field. Anyway, if you compute this sum, this is due to the positive charge, this is due to the negative charge. Sum of them is in here. The electric field E at point P is now computed in this form. Alright, we can make use of the binomial expansion we studied in the last class. In here, this is a general expression, and for example, we have n equals -2, and this kind of form can be written as this, 1/z squared multiplied by this one, and this delta is small. We consider this delta is smaller than z. Then we can make an expansion. Okay, n equals -2 and n minus 1 equals -2 -3. So substituting this result, you will find the binomial expansion. You are not so much interested in the third term and higher. If you consider these two contributions, the leading contribution 1 cancels exactly, and the subleading contribution, this one, has different signs, so they add them up. So this is the 1/a distance squared between plus and point P, z minus 1/2 d squared. Okay, and negative charge, this distance, this is z minus z plus 1/2 d squared, 1/squared. So this difference is found to be 2d over z cubed. Finally, factor of 2 removes the Coulomb force has a coefficient of 4 pi, and this factor of 2 make it 1 over 2 pi instead of 1 over 4 pi. So we have 2 pi epsilon 0. P is the electric dipole moment. As I told you, it is Q times D. Anyway, the electric field due to an electric dipole decays faster than that of a monopole. The electric field due to a monopole decays by 1 over r squared, but the electric field due to a dipole decays by 1 over r cubed. That's the big difference between the monopole and dipole. Okay, let's carry out some further application of the computing electric field. We first consider distribution of charges. Until now, we considered one particle, one charge Q, and plus Q and minus Q, this dipole. What happens if I have charge is distributed plus distributed over a curved wire? Okay. For simplicity, we consider the uniform charge distribution. Delta S, the length. If the delta S contains a charge delta Q and this lambda delta Q over delta S charge per unit length is constant. It does not have to be constant, but for simplicity, we consider constant linear charge density. In case we have a surface charge distribution, we introduce sigma, that is charge per unit area. If the charge is distributed over space, then we use volume charge density, rho, that is a charge per unit volume. For example, we consider the electric field due to a line charge on a circle. Then the line charge density is the charge Q. We consider the case Q is evenly distributed over this circle of radius r. The circumference of the circle 2 pi r. This will be the linear charge density. This lambda equals to dq over ds. Okay, what about ds? ds is r d phi. This is the angle, radial angle about the center of the circle, and we consider small line segment of angle d phi. Okay, then the length of this line segment is r d phi, right? It's r d phi. Now we compute electric field. We compute the electric field due to this small line segment. Small line segment. Small line segment of r d phi. Okay. Then there is a charge dq is placed in here, and then field point. We consider the field point at point 00g. The electric field, because we consider the q is, for simplistic q equals a positive case, electric field is long distraction. But we need to integrate over the circle, thus the contributions will make a kind of cone. So we need to add all these dE differential contribution to the electric field. So we need to compute the electric field by integration. So now QP, this point Q is the source point and P is the field point. Source and field. So the coordinate of this line segment of the circular charge distribution can be written in the form, because the angle, polar angle is phi, x component is r cosine theta, cosine phi, the y component is r sine phi. So substituting this result, QP, what is QP? This P is in here, so Q to P. QP means P minus Q, right? Coordinate of P minus coordinates of Q. So this is x and y minus x minus y plus z. And because of this parameterization, z x square root x squared plus y squared, and this square root x squared y squared z squared are all expressed in terms of this. You know, there is an angle theta that is distinguished this angle theta is distinguished from the angle phi. Right? So, substituting these results, we can do this integral, the following integral. And the integral table is given in here. You can just follow the calculation, and you'll find that the electric field due to a circular charge distribution is like that. In a similar manner, we just restrict the integration angle from 2 pi. This problem does not have semicircle. So this contribution is only half of the previous case, and what we do is to do the same job, except that we have the angular integral restricted to not to pi, but just pi. So once you can evaluate the electric field due to a circular charge distribution, we can generalize this result into a ring. Actually, a circle, a disk of radius r, can be sliced into rings, and its ring can be extended to an annular region, and we'd like to vary this radius from 0 to capital R. Then finally we will find the contribution of the disk for the electric field. That's quite interesting. Again, we use a charge distribution, but in this case it is not a linear charge distribution, instead surface charge distribution. So charge divided by area, pi r squared, is the area of the disk. And area of an annular region, because we consider this with inner circle is of radius r and outer circle is of radius r plus dr, and area of this annular region is 2 pi r dr, right? In here 2r dr is dr squared, and we substitute r equals t. So therefore we can do this integral. This is the contribution of this annular region. Now t equals r squared. We do this integral from r equals 0 through r equals capital R. The integral table can be used to evaluate this integral in such a way. Finally, substituting this integral, we have this kind of electric field. Here we have z over z absolute value. This is either plus or minus, plus 1 or minus 1, right? When z equals positive, z equals negative. So this is actually the sign of z. As r goes to infinity, this next term vanishes completely. Therefore, the electric field due to a disk of radius r goes to infinity, and there's a charge distribution sigma. Is sigma over 2 epsilon 0, sigma over 2 epsilon 0. Magnitude is the same and direction is opposite. So this one is a very, very important, very important expression. Monopole dynamics. We consider the electrostatic force on a charge due to the electric field generated by other stationary slowly moving charges. if a charge is under electric field, the force is QE. Under the same electric field, depending on the sign of the charge, the direction of the force flips. This is an example of finding the unit of the elementary electric charge carried by the Millikan, so-called Millikan all-drop experiment. Okay. Millikan first measured the electric charge E. It is now confirmed, and it is now determined to be, it is defined to be 1.602176634 times 10 to the minus 19 Coulomb. Now we mostly use the laser printer. Inkjet printer uses this kind of electric field to deflect the charged ink to change its destination on the paper. This can be done by changing the electric field between the two parallel plates. And let's see. An ink drop of mass m, tiny mass, and some charge much bigger than the elementary electric charge. Electric field is given this y direction along electric field is downward, that means minus parallel to minus j direction. The magnitude of the electric field is given in like this. The initial velocity of the drop is 18 meters per second along the x-axis. We neglected gravitational force and drag force. Okay, the acceleration of the drop can be computed by multiplying the charge to the electric field. So QE, and acceleration is divided by force divided by mass. The result is given in here. Takes time t for drop to reach. You can compute this uniform acceleration. We have neglected the gravitational acceleration, so this the acceleration is solely due to the electric field, electrostatic field force. Dipole dynamics. If dipole is, for example, the center of mass of dipole, and you fix the center of mass and let it place the pivot so that it can rotate in either direction depending on the torque on the system. We have plus charge Q and minus charge Q. If the electric field is applied, and here, electric field, F equals QE. This is positive though. So F plus is in this direction. Because this is negatively charged particle and amount is the same, we have the same force except for the direction. The direction is opposite. So sum of these two forces is 0. Net force equals 0. However, net torque is non-zero. So, in this system, it wants to rotate along this direction. What happens if this positive charge is below, for example, in this case? Again, force is along the same direction. However, the torque is along this direction. So in this case, therefore, there is some equilibrium position. This in here, the system wants to return, converge this point. This is a stable equilibrium position. Okay? So due to this, there should be a small oscillation. If the energy is not large enough, if there is a small, tiny energy above this ground state, then the system makes an oscillation. Thus, the torque can be computed in this way. We remember this is d. Displacement vector from negative charge to the positive charge is d. In that case, the torque can be computed separately, 1/2 d, and this is minus 1/2 d. Because of this, we can compute the torque on the positively charged particle and negatively charged particle. And sum of the torque is computed in this way. So that is d cross E, Q. And QD is the electric dipole moment. So the answer is the torque is P cross E. And once we know the torque, we can compute the corresponding potential energy. We have force. We can compute the potential energy. We have the torque, that we can compute the corresponding potential energy. The rule is this. And substituting this result in here, you'll find that the answer is depending on the cosine, minus cosine theta. And here, the constant piece does not have to be considered because its a derivative only contribute to the torque. This constant is unnecessary. So the corresponding potential energy can be expressed as minus PE cosine theta, where angle theta is this angle between the electric field and electric dipole moment. So the torque is P cross E, and the corresponding potential energy P dot E, scalar product. You can apply this result to consider interesting problem. So you can click this. You find there is a destination. Okay. You will find a very interesting integral table involving the calculation we have done today. Okay, that's it for today.